This is the screencast for section 3.5, example 6. So in chemistry, the acidity of a water-based solution is measured by the concentration of hydrogen ions in the solution in moles per liter. The hydrogen ion concentration is written H+, so that's what the H+ means there. Because such concentrations usually involve negative powers of 10, so 10 to the negative something, negative orders of magnitude, which we just learned about in the last section, are used to compare acidity levels. The measure of acidity used is pH, which I'm sure you've heard of from not only me, your science teachers, and I don't know, Mr. Nye the science guy or something. The opposite of the common log of hydrogen ion concentration. The opposite of the common log of the hydrogen ion concentration. More acidic solutions have higher hydrogen ion concentrations and lower pH values. Okay, so example 6, let's compare the chemical acidity of two substances. Some especially sour vinegar has a pH of 2.4 and a box of leg and sickle baking soda. Really? Leg and sickle? Think about it. What's the most famous kind of baking soda you know? That's right, Arm and Hammer. Leg and sickle. A sickle is one of those things that Grim Reaper uses in a cornfield kind of thing. Anyway, okay. So what are their hydrogen ion concentrations? So we're going to solve for H+. So let's try the vinegar first. The vinegar has a pH of 2.4, and that equals the opposite of the common log of its hydrogen ion concentration. So we just need to solve for H+. So I'm going to divide both sides by -1. So negative 2.4 equals now just the regular log of H+. And I'm going to do the go-to, change this to exponential form. So this is log base 10, so now the base of my exponent is 10. And then logs find exponents, so the output of this log is negative 2.4. And that's going to equal the hydrogen ion concentration. 10 to the negative 2.4 is about 3.98 times 10 to the negative 3 moles per liter. I will accept 10 to the negative 2.4, no problem. For you science buffs out there, either one is perfectly acceptable. So that was the vinegar. Now let's do the leg and sickle baking soda. The baking soda has a pH of 8.4. So that would equal the opposite of the log of its hydrogen ion concentration. So divide both sides by the negative. Negative 8.4 equals the log of H+. Then the base of my log is 10, which becomes the base of my exponent when changing this to exponential form to solve for H+. 10 to the logs find exponents, so the output, negative 8.4, becomes the exponent. That is H+. So that is a perfectly acceptable answer. Or you have 3.98 times 10 to the negative 9 moles per liter. Part B asks, how many times greater then is the hydrogen ion concentration of the vinegar than that of the baking soda? Well, how many times greater would be similar to what we did in the earthquake. We're going to divide by how many. We're going to divide by their intensities. So I'm going to take the intensity of the vinegar. Well, wait, intensity with earthquakes. Vinegar is not intense. The hydrogen ion concentrations. So 10 to the negative 2.4 over 10 to the negative 8.4. That is 10 to the negative 2.4 minus negative 8.4 is 10 to the 6th. So you're talking about a million times greater. So C, by how many orders of magnitude do the concentrations differ? So what power of 10? 6 orders of magnitude. Then I'll try problem number 47. Says the pH of carbonated water is 3.9 and the pH of household ammonia is 11.9. So part A asks us to find the hydrogen ion concentrations. So I'm going to set up both the water and ammonia and find their hydrogen ion concentrations. So in setting each of their pHs equal to the opposite of the common log of their hydrogen ion concentrations, I was able to divide both sides by -1, change to exponential form, and again, either answer would be acceptable. 10 to the -3.9 is the hydrogen ion concentration, which is 1.26 times 10 to the -4 moles per liter for the water. And then 10 to the -11.9, which is the hydrogen ion concentration, which is 1.26 times 10 to the -12 moles per liter. How many times greater is the hydrogen ion concentration of the carbonated water than that of the ammonia? So I'm going to put 1.2, oh no, I'm not. So I'm going to put 10 to the -3.9 over 10 to the -11.9, which is therefore 10 to the -3.9 minus -11.9 when I'm dividing by the same base. I subtract the exponents. So that would be 10 to the 8th. Wow, so that's 1, 2, 3, 4, 5, 6, 7, 8. So you're looking at 100 million times greater concentration. By how many orders of magnitude is that? Wow, way easier to use orders of magnitude. That's 8 orders of magnitude.